Hello everyone, I am Samuel Teodoro and today I will be presenting to you this newer IPS 2020 paper called Robust, Accurate Stochastic Optimization for Variational Inference. Here are the contents of my presentation. I will first give you an introduction of the paper. So Bayesian inference has become a popular approach in machine learning due to its flexibility and theoretical foundation in probabilistic reasoning. The central object in this approach is the posterior distribution, which is the distribution of the parameter of interest given some data. Here we are required to approximate the said posterior distribution. Now, variational inference is also become a commonly used approach for large-scale approximation or approximate inference in machine learning due to its computational efficiency. Here, we compute an optimal variational approximation Q star, which is equal to argmin Q in Q of the divergence of Q and P. Now, the variational family is often parameterized by a vector lambda in Rk. So the parameters of Q star is given by lambda star, which is equal to argmin lambda in Rk of the divergence of Q lambda and P. Now, variational inference is becoming an attractive statistical method since the variational approximation can often be computed more efficiently than either the maximum likelihood estimate or more precise posterior estimates. And recently, there have been two developments that have greatly increased the scope of applicability of variational inference methods. They are the stochastic variational inference and the black box variational inference. Let us first take a look at the stochastic variational inference. So here, we try to solve lambda star using stochastic optimization with mini batching. So with the help of mini batching, we this allows us to scale to data sets with tens of millions of observations. The black box variational inference, on the other hand, have extended variational inference to a wide range of models in probabilistic programming context. This is achieved by removing the need for model-specific derivation, making our approach flexible. However, despite the flexibility and the scalability, it is difficult to solve the optimization problem with sufficiently high accuracy, particularly as the dimensionality of the variational parameter lambda increases. And aside from that, our existing optimizers today are very fragile. That is, they require the choice of many hyperparameters and they can fail badly. So as a solution, this paper addresses the shortcomings of current stochastic optimizers for variational inference by viewing the underlying optimization algorithms as producing a Markov chain. So, uh, this Markov, this Markov chain perspective allows us more accurate variational parameter estimates by using what we call the iterate averaging. So this iterate averaging is very effective in high dimensionality settings. Again, there are still drawbacks to this approach. The problems of fragility remain even when using this iterate averaging. And in particular, there is a need to determine first when to start averaging or when the optimize or determine when the optimizer has failed. And B, when to terminate our optimization. Now, in this paper, they tried to address the first problem using the R-hat diagnostic. And they tried to address the second problem using the Monte Carlo standard error or MCSE estimates. I will further explain these two in the succeeding slides. But first, let us take let us first take a quick look at variational inference and other concepts that we will need in this presentation. So in variational inference, we let P of y and theta denote the joint density for a model of interest, where y in Yn is a vector of n observations, and theta in Rp is a vector of model parameters. Here, our goal is to approximate the resulting posterior distribution, P theta, by finding the best approximating distribution Q in the variational family Q as measured by a divergence measure. And as we learned in class, we by minimizing the KL divergence, uh, we are also maximizing the function known as the evidence lower bound or the elbow, which is given by the following formula. Here, Q is parameterized by lambda in Rk, and Li of lambda is equivalent to the following expression. Now, the optimal approximation here is Q lambda star, for lambda star equal to R max lambda of L lambda. Now, in stochastic optimization for variational inference, we approximately find lambda star using the stochastic optimization scheme given by lambda t plus 1 equal to lambda plus eta gamma t g hat t. And g hat t is an unbiased stochastic estimator of the gradient L at lambda t. Eta is a base step size, and gamma t, which is greater than 0, is the learning rate at iteration t. The shortcomings of stochastic gradient descent recently have led to the development of more robust adaptive stochastic optimization schemes, such as RMS prop, ADAM, and ADAGRAD. However, despite using these stochastic adaptive stochastic optimization schemes, it still remains trivial to check for convergence. And usually we do this by using the delta elbow stopping rule. However, using this stopping rule can still be problematic, as the scale of the elbow makes it non-trivial to specify a universal convergence tolerance epsilon. So sometimes the objective estimates are too noisy, so this results to the stopping rule never triggering. Sometimes epsilon is also too large, and this makes our stopping rule trigger at an earlier time. Next, we also need to refine a variational approximator, because another challenge in variational inference is assessing how close our variational approximation Q lambda of theta is to the true posterior distribution P. Here, in this case, we use the K-hat diagnostic. And in this diagnostic, we let theta 1 to theta s sampled from Q lambda denote draws from the variational posterior. Now, using the importance sampling, we can estimate an expectation under the true posterior given by the following expression. And here, our weights, W theta s, is equal to P theta s given y over Q theta s. And we note that if our proposal distribution is far from our true posterior distribution, the weight W theta s will usually have a high or a very high or an infinite variance. So now that we have taken a brief look at these concepts, We can now take a closer look at the approach this paper proposes, which is viewing the stochastic optimization as producing a Markov chain. And in this paper, the authors tried to improve the optimization accuracy by using iterate averaging. And as I've mentioned earlier, in high dimensional settings, we should not expect that a single iteration, lambda t, to be close to our lambda star. So this paper proposes using iterate averaging, or IA, to construct a more accurate estimate of lambda star. And it is given by the following expression where our lambda bar is equal to the mean of lambda t plus I. Here, our aim is to choose t that is greater than or equal to t0. So our t0 is the point where we will reach stationary distribution. Now, I've mentioned earlier that to make the iterate averaging more robust, the authors of this paper tried to determine when to start and when to stop averaging. So, as I've mentioned, they addressed starting when to start averaging by using the R hat diagnostic. Um, they also use the MCSE to address when to stop averaging. And now I will be explaining both of these measurements. I will first start with the R hat statistic. So the R hat statistic is a canonical way to determine whether a Markov chain have reached its stationarity. And usually we do this by computing R hat of multiple Markov chains. So given J chains, n iterates in each chain, and lambda ij such that I is from 1 to n and j is from 1 to j, then our R hat diagnostic or statistic is given by the following expression. And here, our V hat is the between chain variance, and the W hat is the within chain variance. Next, we need to know when to stop averaging. So in this paper, they proposed a stopping criterion, which is called the Monte Carlo Standard Error, or MCSE, given by the following expression. And here, V of lambda I is the variance of the ith component of the iterates. And ESS of lambda I is the effective sample size, or ESS, which is equal to Jn over the quantity 1 plus the summation from 1 to infinity of 2 rho t. So in the previous expression, n is the number of iterations after the R hat convergence, and rho t is the autocorrelation of lag t. And in summary, here is the proposed algorithm of the paper. Here, the authors used a learning rate eta of 0.01, a window size W of 100, an R hat cutoff tau of 1.1, and an ESS cutoff of ESS cutoff E of 20. Now let us take a closer look at this graph included in the paper. So in the y-axis, you can see the distance d between the variational and ground truth moments for a full rank variational inference approximation on linear regression models of varying dimensions of posterior. And in the x dimension, we can see that, in the x-axis, we can see the dimensions of variational parameter k. So the blue lines, both the solid and the dotted line, show um, the standard stopping rule, which is the delta elbow. And the red lines, both the solid and the dotted red line shows the proposed method, which is the MCSE stopping rule. And both the dotted lines, the blue one and the red one, indicate that they used iterate averaging in that case. And as you can see, the red dotted line managed to improve the accuracy, particularly in the higher dimensions, because the distance between the variational and the ground truth, uh, well, because the test was sorry because the test was able to record a very low distance between the variational and the ground truth moments. So as you can see, it was very effective in improving the accuracy. So that is it for my presentation. Thank you very much for listening.